Welcome to this first video of a playlist about the preparation of piperidines. You can find a PDF version of this video under the Community tab of my channel. In this video we'll have a look at the most practical ways to prepare piperidines with alkyl or aryl substituents at position 2. The other videos of this playlist are about piperidines with substituents at positions 3 and 4. There is a bit overlap between the videos, so you may check all three just in case. Piperidines behave as typical secondary or tertiary amines, and you may also have a look at my videos about the alkylation of amines and about the synthesis of aryl amines and phenylethylamines for further synthetic inspiration. The name piperidine comes from the Latin name of black pepper, Piper nigrum, the plant from which a piperidine derivative was first isolated. The compound which causes the sharp taste of pepper was called piperine and later identified as an amide of a 6-membered cyclic amine, then called piperidine. Other degradation products were piperonal and piperic acid. Many plants and animals produce alkaloids with piperidine substructure to kill or scare herbivores and other assailants. Here's a selection of natural piperidines, but there are many more. Also, many synthetic drugs are substituted piperidines. These compounds are metabolically sufficiently stable and show good oral bioavailability. Unfortunately, most are chiral, what complicates their manufacture. Piperidines with substituents at position 4 are not chiral and thus easier to prepare and are often preferred for drug discovery. But right now we'll focus on piperidines with substituents at position 2. Pyridines are the most convenient starting material for piperidines, and you may check my videos about the synthesis of pyridines for further ideas. Treatment of pyridines or pyridinium salts with carbon nucleophiles can yield 2 substituted dihydropyridines, which are easy to reduce to piperidines. Alternatively, 2 alkyl or aryl pyridines can also be prepared from 2 chloropyridine. Pyridines can be reduced to piperidines chemically or by catalytic hydrogenation, often with high stereo and regioselectivity. I'll show you specific examples in a minute. A further convenient starting material is 2-methylpyridine, which is quite acidic at the methyl group and readily undergoes condensation, acylation, and other CC bond-forming reactions. More difficult is the metallation of piperidines at position 2 by strong bases, followed by treatment with carbon electrophiles. Oxidation of piperidine yields an imine, which can be converted into substituted piperidines by treatment with carbon nucleophiles. Even carbenes have been used to alkylate piperidines at position 2. Such reactions often proceed by hydride abstraction, as sketched here. Let's check some specific examples of these strategies. Here, tertsbutylithium added mainly at position 2 of pyridine and gave a mixture of mono and dialkylated products. Unfortunately, however, such additions can also occur at position 4. Pyridinium salts are more electrophilic than pyridines and often easier to alkylate and to reduce. Here, a Grignard reagent added to N-methylated methylnicotinate, mostly at position 6. The ester remained unchanged, despite the excess of Grignard reagent, probably because of its deactivation by the conjugated amino group. With the aid of enantiomerically pure catalysts, such reactions can yield non-racemic products. Here, the carbon nucleophile was a boronic acid and the arylation was catalyzed by a chiral rhodium complex. Pyridones, like the product shown here, can be prepared from 4-methoxypyridine by activation with a chloroformate followed by reaction with a carbon nucleophile. In this example, a chiral copper diphosphine complex catalyzed the addition of ethyl magnesium bromide to the intermediate pyridinium salt. As an alternative to chiral catalysts, pyridines can be activated by acylation with an enantiomerically pure acyl chloride, as in this example. Addition of a Grignard reagent at position 2 proceeded with high diastereoselectivity in this case. Terminal alkynes do not need to be metallated stoichiometrically to add to pyridinium salts. Here, a combination of zinc chloride and a tertiary amine was sufficient to bring about the alkynylation. In this example, ketene was generated from acetyl chloride and sodium hydride in an excess of pyridine. A mixture of two regioisomeric dihydropyridines resulted. Pyridine N oxides are less electrophilic than pyridines or pyridinium salts, but do still react with polar organometallics. Here, phenyllethium added enantioselectively to 4-phenylpyridine N oxide, and the initially formed dihydropyridine was reduced with sodium borohydride to an N-hydroxy tetrahedropyridine. The starting material of this example was an aminopyridinium illite, and it reacted with methyl magnesium bromide in the same way as a pyridine N oxide. This here is a typical example of the condensation of 2-picoline with an aldehyde followed by quaternization and hydrogenation. The low hydrogenation yield was due to intramolecular addition of the aniline to the partially reduced pyridine ring. Enantioselective hydrogenations of pyridinium salts have also been reported. In this example, a soluble iridium catalyst was used, also to prevent hydrogenolytic debromination. The cyano group remained unchanged as well. With 2-propylpyridinium salts, these conditions gave a slightly lower enantiomeric excess. Much higher enantioselectivities could be attained by heterogeneous catalytic hydrogenation of enantiomerically pure 2-aminopyridines, as shown here. The starting material of this reaction, however, was more expensive than those of the previous examples and also required stoichiometric amounts of a chiral auxiliary. The hydrogenation was conducted in acetic acid to prevent poisoning of the catalyst by the basic nucleophilic reactants. Enantiomerically pure 2-alkylpyridines can sometimes be hydrogenated with high diastereoselectivity. In this example, the pyridine ring was hydrogenated faster than a substituted quinoline. Some pyridines are difficult to hydrogenate, in particular those which form strong complexes with transition metals, such as 2 or 4-aminopyridines or 2-aminomethylpyridines. These compounds tend to poison most catalysts, in particular if the hydrogenation is conducted under alkaline conditions. In such instances, hydrogenation with an excess of a strong acid or a reduction by metals or by hydroboration may be more successful. Here, a pyridine was hydrogenated with the aid of boranes, without any transition metal catalyst. The benzophenone substructure remained unchanged. Here, 2,4-lutidine was reduced with an excess of sodium in ethanol, like in a Beauvais-Blanc reduction. A mixture of piperidines and tetrahedropyridines resulted. The reduction was completed by hydrogenation with catalytic platinum oxide under acidic conditions. Few examples of such reductions by metals have been reported though, because pyridines readily dimerize after intermediate radical anion formation. I'll show you some examples when discussing side reactions at the end of this video. Another strategy for preparing 2 substituted piperidines is by oxidation of piperidines to imines, followed by addition of carbon nucleophiles. In this example, the imine was generated by chlorination with NCS, followed by base-induced elimination. A proline-catalyzed enantioselective Mannich reaction with acetone then yielded the target piperidine, with 94% enantiomeric excess. Lithiated piperidines are sometimes dehydrogenated by electron-deficient ketones. In this example, trifluoroacetophenone was used, and the resulting imine reacted with an ester enolate to yield methylphenidate. This example is similar to the previous one. Here, lithiated benzyl chloride was added to the imine, and a low yield of a polycyclic piperidine resulted. Also, piperidine-derived nitrones can be suitable starting materials for substituted piperidines. Here, an enantioselective Mannich reaction with acetophenone yielded first a hydroxylamine, which was reduced to the piperidine with zinc in acetic acid. Unfortunately, the required nitrone is tricky to make and yields tend to be low. In this case, piperidine was oxidized with hydrogen peroxide and catalytic selenium oxide. Protected piperidines can be lithiated with a strong basis at position 2, and the resulting carb anions react with various carbon electrophiles to the expected products. Here, the electrophile was benzaldehyde, and the resulting benzylic alcohol was deoxygenated by hydrogenolysis. The piperidine was resolved with a carbamate of lactic acid. In this example, a substituted piperidine was lithiated with sec-butylithium and then methylated with dimethyl sulfate. Deprotonation occurred at the methylene group only, and the alkylation proceeded with high diastereoselectivity. Metallated piperidines can also undergo palladium-catalyzed arylations or vinylations, as shown here. The regioselectivity of these reactions is uncertain, however, because the intermediate 2-palladated piperidine can rearrange into a 3-palladated piperidine and lead to piperidines substituted at position 3. I'll show you an example in part 2 of this playlist, where the conditions were almost identical to those shown here. It could also be that the structural assignment in this example is wrong, and the product may have been a 3-aryl piperidine instead of the proposed 2-aryl piperidine. Here, 2-phenylpiperidine was prepared by addition of phenyllithium to bromovaleronitride, followed by reduction and protection. This product was then lithiated enantioselectively at the benzylic position and then carboxylated with a chloroformate. Yield and enantioselectivity weren't high in this case, but the strategy might be optimizable for other piperidines. 2-cyanopiperidine can be prepared from piperidine by dehydrogenation and addition of cyanide to the intermediate imine. Here, after benzylation at nitrogen, this cyanopiperidine was lithiated and then alkylated with an alkyl bromide. Reductive decyanation was achieved by treatment with a lithium biphenylide. Thus, the cyano group acted as a transient acidifying group. This here is another interesting strategy for preparing enantiomerically enriched piperidines. Enantiomerically pure alpha-methylbenzylamine was first converted into a 2-cyano-tetrahydropyridine by partial reduction and cyanation of an intermediate pyridinium salt. Lithiation, alkylation, and reductive decyanation then gave a mixture of 2 diastereomeric tetrahydropyridines, which can be converted into coneine by catalytic hydrogenation. Tetrahydropyridines are more acidic than fully saturated piperidines and easier to lithiate. Here, an enamine-derived urea was rearranged by treatment with LDA. A remarkable aryl group migration occurred with high regioselectivity. A similar allylamine-derived urea could also be rearranged under these conditions, but a 2,6-diphenyl tetrahydropyridine resulted instead. So, the predictability of this chemistry isn't great. Examples have also been reported of the alkylation of piperidines by intramolecular carbene CH insertion. In this example, the carbene was generated by heating a tosyl hydrazone with potassium terzbutoxide, and the insertion proceeded with high diastereoselectivity. Instead of metallating a protected piperidine or tetrahydropyridine, electron-deficient pyridines can also be alkylated directly and then hydrogenated. In this example, the starting pyridine was converted into a radical anion with sodium naphthalenide and then alkylated with an alkyl iodide. After a second alkylation at nitrogen, the resulting dihydropyridine was hydrogenated to an enamine. Reduction with borohydride would probably have yielded an allylamine, as in some of the previous examples. Unfortunately, this chemistry only works well with acceptor-substituted pyridines. 2-pyridones are valuable intermediates for substituted piperidines or piperidinones. Sometimes 2-pyridones react with carbon nucleophiles at position 6, as in this example. Addition at position 4, however, can also occur. The starting pyridone of the previous slide can be prepared by oxidation of quaternized pyridine, for instance with hexacyanoferrate. As an alternative, 2-hydroxypyridines can sometimes be alkylated selectively at nitrogen with soft alkylating agents, for instance with Michael acceptors. Glutaroimides may also be suitable starting materials for substituted piperidines. In this example, an excess of Grignard reagent was added to a glutarimide to yield a ketone as a mixture of open-chain ketone and cyclic aminal. Reduction with triethylsilane gave mainly one diastereomer of a piperidinone. Tetrahedropyridines can also be converted into epoxides and then alkylated with a carbon nucleophile. Here, the epoxide was generated in 2 steps by hydroxybromination and base-induced ring closure. Reaction with allyl magnesium chloride then yielded the target piperidine. There are several ways to rearrange furfural into 3 pyridones. Furfural is prepared by heating carbohydrates with an acidic catalyst. In this example, a tosylated aminomethylfuran was rearranged by oxidation with chloroperbenzoic acid. After etherification, an acid-catalyzed allylation with an allylsilane yielded a substituted pyridone, which might have been further reduced to a piperidine. This strategy thus enables the preparation of 3 pyridones with 2 different substituents at positions 2 and 6. Also, pyridines can rearrange to piperidines. Here, a hydroxymethylpyridine was first converted into an aziridinium mesylate with methane sulfonyl chloride and then treated with an excess of acetate. The target piperidine was obtained in high yield and with high stereoselectivity. Cycloproponated pyroles can react with carbon nucleophiles and yield substituted dihydropyridines. In this example, a 2-aryl dihydropyridine resulted, which was reduced to the piperidine by catalytic hydrogenation and a final acid-mediated reduction with triethylsilane. I'll show you now some examples of cyclization reactions that yield 2 substituted piperidines or close precursors. Sorbic acid, the starting acid of this example, is produced on a large scale from crotonaldehyde and ketene as a biocide for the preservation of food and many other products. Thus, it is inexpensive and readily available. Strong heating with primary amines yields either dihydropyridones or 4-aminopyridinones. The latter can probably be transformed into the former by quaternization, nitrosation, acylation or sulfonylation of the amino group and elimination. Lysine is a potential starting material for the preparation of piperidine 2-carboxylic acids. Treatment with nitrite only gave a low yield of this product, however, but perhaps this reaction can be optimized further. Here, lysine was converted into 2-aminomethylpiperidine in 4 steps. The overall yield was about 50%, slightly higher than in the previous example, but the synthesis took almost a week. The key step was the formation of an aziridinium salt and cyclization to a piperidine. One elegant method to prepare piperidines is by addition of carbon nucleophiles to halovaloronitriles or to imines of halopentanal. The latter can be obtained from dihydropyrane, which in turn is made by heating tetrahydrofurfuryl alcohol. In this example, such an imine was treated with an excess of Grignard reagent, first at -20 degrees Celsius and then at room temperature. Intramolecular alkylation at nitrogen required an additional base. The chiral auxiliary provided for some moderate stereocontrol of the addition of the Grignard reagent to the imine. Protected pentanyl amines can be cyclized by treatment with electrophilic halogenating reagents. In this example, such a reaction was conducted in the presence of 10% of a quinine derivative, and the cyclization proceeded with moderate enantioselectivity. The product was converted stereoselectively into a 3-phenyl piperidine by treatment with silver salts. Also protected pentynyl amines can be cyclized. Here the intermediate enamine was reduced to the final piperidine with triethylsilane and acylyl triflate. In this example, a homoallyl amide was treated with hexanal and an excess of trimethylsilyl chloride. A Prince-type reaction yielded mostly one diastereomer of a protected 4-chloro-2-pentylpiperidine. Glutaraldehyde can be cyclocondensed with imines to yield tetrahedropyridines. When conducted in the presence of proline, high enantioselectivities can sometimes be attained, as in this example. The initial condensation product was oxidized in situ with a slight excess of 2-iodoxybenzoic acid to a dihydropyridine. Reduction with borohydride and oxidative deprotection then gave the final tetrahydropyridine. Another cyclization strategy is by oxidative benzylic amination. The sulfonylamine intermediate was moderately electrophilic only, and carbocation formation by hydride abstraction only worked well with electron-rich arenes. Imines can act as electron-deficient dienophiles in hetero-Diels-Alder reactions. These reactions proceed faster the more electron-rich the diene and electron-deficient the imine. Here, the imine was generated in situ in the presence of isoprene and an acceptable yield of mainly one regioisomeric tetrahydropyridine resulted. Lewis acids can catalyze Diels-Alder reactions. In this example, 1% of a cobalt porphyrin was used and the reaction was complete after only 2 hours at room temperature. With the aid of a chiral palladium complex, these reactions may even proceed enantioselectively. In this example, 76% enantiomeric excess was attained, along with a good diastereoselectivity. Cycloaddition of the Daniszewski diene to imines yields pyridones like the product shown here. These are valuable intermediates for preparing substituted piperidines. If the imine is part of a 1,3 diene, as in this example, the diene will be electron deficient and the dienophile must therefore be electron rich for a Diels-Alder reaction to proceed. Here, the reaction was catalyzed by a rhodium complex and the initially formed enamine was reduced with borohydride to a tetrahydropyridine. Pyridones can also be obtained by condensing beta-amino esters with beta-keto esters, as in this example. Catalytic hydrogenation yielded in this case a tri-substituted piperidine. Let's check some potential side reactions. I showed you an example of the reduction of dimethylpyridine to the piperidine with sodium. Such reactions can, however, also yield dimerized pyridines by intermediate formation and dimerization of pyridyl radical anions. Here, the dimerization was conducted in the presence of air, and a bipyridine was therefore obtained. Without oxidant, the products would be dimerized, partially reduced bipyridines. In this example, the dimerization was brought about by magnesium and catalytic sodium, and the oxidation by nitrobenzene. Also, pyridinium salts can dimerize. In this example, cyanide was used to promote the dimerization. The herbicide paraquat has also been prepared on an industrial scale by a cyanide-induced dimerization of N-methylpyridinium salts. Here's a selection of mostly newer references, which you can also find in the description of this video. Under the Community tab of my channel, there's a PDF version of the slides. The next video of this playlist is about the preparation of piperidines with a substituent at position 3. See you!